Okay, so let me say a couple of words for the next one. Okay, right. So in the first problem, we're going to let G and H be finite groups. Finite is important here. With the order of G and the order of H relatively prime. That's also going to be important. This is part of the problem. Show that G and H respectively can be identified with characteristic subgroups of G cross H. I mean, I think you can probably guess which ones, right? G would be identified with G comma identity and so forth. Show that in this case, and you're going to need these assumptions here because this in general is true. Show that ought of G cross H is ought G cross ought H, right? So if you have two cyclic groups relatively, or if you have two groups relatively prime order, finite groups, then the automorphisms come that way. Number 3, show that if G is cyclic, then the automorphism group G is abelian. So if you got a cyclic group, then you've got then the automorphism group is abelian. Notice this is not true if G is not cyclic. For example, I think last homework or the homework before, you looked at the automorphisms of C2 cross C2 and C2 cross C2 cross C2. These groups are both very abelian. Notice they're not cyclic, but their automorphism groups are not abelian. If G is cyclic, does it follow that the automorphism group G is cyclic? Prove this or you can counterexample. Number 2, suppose that G is a group and H is a subgroup of G of index n. Show if no non-trivial normal subgroup of G is contained in n, then G is isomorphic to a subgroup of S n. So, right. So this should follow from some of the stuff that we did last time. If you've got a normal subgroup of index n, and you've got no non-trivial normal subgroup of G contained in H, well, of course, you always have the identity contained in H, but nothing non-trivial is in there. So G is isomorphic to a subgroup of Sn. And B, you all remember this old chestnut. We talked about this in class, and I'm sure you've heard before. If you have a group G and it's got a subgroup of index 2, it's always normal, right? That's kind of an old chestnut, right? Here's a generalization of this. If G is a finite group and it's got a subgroup of index P where P is the smallest prime dividing the order of G, then it's normal, right? That's kind of a nice generalization. Notice that you can remove all this P is the smallest prime dividing the order of G if P is 2 because P is, or 2 is the smallest prime. So this generalizes. So if you have like some odd order group and P is the smallest prime dividing it, and you happen to have a subgroup of that index, it's got to be normal. Number 3. 3 should be actually, I think, pretty easy. Let G act on a set. The action of G on S partitions S into disjoint subsets. Find the equivalence relation that does this, because every partition corresponds to an equivalence relation, and describe this induced partition. And 4 and 5, we're kind of going to get practical and put some of this work together. Classify all groups of order P squared, where P is a positive prime. An earlier homework problem also might be useful in going down the path for this one. By the way, I know 2 of them, right? The abelian ones, Z mod P squared and Z mod P sum Z mod P. Are there others? Classify all groups of order 8. By the way, I know 3 abelian ones. Z2, 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 Z4, Z8. You should be able to find some others that are not abelian. Okay, any questions on that? Any questions? I think this ought to be a fun little homework. So, okay, let's pick up where we left off last time. we last talked about this theorem where basically every a group can be identified as a group of permutations, right? Let's give a corollary to this. 15, let G be a group. A for all G G induces G. We've already developed this. This is sort of just for recording in your notes. We've sort of developed this anyway. This is what we call B sub G, where B G of X. And B, there exists a homomorphism B G and again, we've already kind of, we're recording this sort of for your notes, but you can get the proof from the homework. It's got this in it. That homework problem. And let me make this statement here. I've already done the class equation. We did it last time in sort of a more raw form. Here's the form that you may be more familiar with.
That's one of them will be the limit of phi.
What's that now?
The bracket, yeah. The limit phi or limit G.
No, this is something you proved in the homework, actually, that comes from this. This homomorphism, actually, this is really kind of bad notation. Let me call this F, because I don't want you to confuse it with this B. This F takes an element G and gives you phi G, this thing. That's the automorphism. Every one of these is called an inner automorphism. So the image of this doesn't necessarily cover all the automorphisms. It only covers the inner automorphism. Kernel is center. So this is from an old homework problem that G mod the center of G. That's the kernel of this automorphism. It's isomorphic to the inner automorphism of G.
We use the first isomorphism.
Yeah.
So the image should be F, right?
No, because it's not necessarily onto. Right. This is the image. Right. This is actually a subgroup. And the subgroup is precisely the image of this map, right? Because the correspondence takes every element G and it goes to this one of these phi G's, which is an inner automorphism. So, for example, I'll give you a good example. If G is an abelian group, then every inner automorphism is trivial, right? Because everything commutes, right? And so, for example, if you have something like Z2 sum Z2, then this automorphism is trivial. And no surprises here, the center of Z2 is the whole thing. And so you get the identity is isomorphic, the identity, which is very useful in that particular case. So here's the class equation. Well, so it's finite. going to say for x1, x2, up to xk, our representatives okay. This is what the class equation was. In fact, in the class equation, what we did is we just wrote the sum here, right? But what I've done is I've pulled out everything in the center, right? So if you have one of these x's in the center, then its conjugacy class is just itself, because when you conjugate anything in the center by anything, it just leaves it alone. So here we're counting, what we're doing is we're counting, these are all the conjugacy classes that just have one element in it, and that's exactly the center of G. And these are the fun ones that have more than one conjugate, right? So this is the same as we did before. It's perhaps a little bit easier to see this. Let me give you this is an incredibly important corollary. G is prime. Then center of G this is an amazing theorem because what it says is that you have a group, if you have a group of order P to the n, then it's always got something in the center other than the identity, because that's a strict inequality. So that means if you have any group order P to the n, there's something, at least one thing, that commutes with everything. Right? This is amazing. Just look at S3, right? Just S3. There's nothing in S3 except for the identity that commutes with everything. This is true in Sn. And sometimes the center is very small. By the way, how many of you have ever played with the Rubik's Cube? Anybody know what the center and back group action is? There's only two elements in the center. There's only two moves on the cube. One of them is the identity. Anybody know what the non-trivial one is? What's that?
Something that involves the center.
That's right.
The center of the nine. That is not the center.
The super flip. You know what the super flip is? It's where you've got 12 side pieces, right? It's only got two colors on them, right? So if you look at a Rubik's Cube, so the center is sort of, the smaller the center is, sort of the more non-abelian your group is. You might sort of think of the measure this way. Take every one of these pieces, I'll call them side pieces, because they're the side pieces are the ones that only have two colors on them, right? Now imagine that you can take all these, imagine that God reaches down and takes all of them, takes them out, turns them around, and shoves them back in. That's the super flip. It just flips every one of these in orientation. Right? Now, if you think about that for a minute, if you do your magic to a cube, and then you pull out all those 12 pieces and flip them, it's the same thing as flipping them in the first place and then doing the move, right? Now, it's not really, that's probably not, doesn't make it 100% clear that it's in the center, but it seems like that should be the case. And it's certainly not clear that that's the only thing other than the identity in the center, but actually, it's true. And this has like 4.3 times 10 to the 19th elements in it, right? And only two of them are commute with everything, which is kind of small. But this corollary says if you've got a group of order P to the n, you've always got in fact, actually, the center is usually pretty robust, actually. By the way, this means if you have you ever seen like the baby Rubik's Cube that only has 2 on it, right? And then that means the only center, and that's got like 4 million elements on it or something like that. That means the center is only the identity there because there's no way you super flip that. Proof. Suppose the order of G, here we'll send it in as 1. I guess I should written that in a corollary. Look at the class equation. Now, let me make a couple of observations. First of all, the order of G is P to the N. And so the order of the centralizer in G, Xi, is P to the K, where K is less. Why strict? Why is the centralizer of each one of these Xi's over here strictly less than the end?
The center is not.
Okay. Well, so remember how these elements are picked. These are representatives of the non-trivial conjugacy classes, right? So ask yourself this: what happens if K equals N? That means the centralizer of Xi is the whole group, which means it's in the center, which means I'm not counting it over here. Everybody okay with that? So everybody okay with that? And the fact that it has to be of the form P to the K is Lagrange's theorem, because this is a subgroup, and so it must be a power of P less than or equal to N, and now we don't strict with S. Therefore, the order, or I'm sorry, the index here, the N minus K, which is divisible by P, because N minus K is 0. Right. So let's pick this apart. What this means is this is divisible by P, because you're adding up a whole bunch of garbage. It's all divisible by P. This is divisible by P, in fact, to the N. Therefore, the order of CG is divisible by P and is greater than or equal to 1. So the order of the center can't be 0, right? But it's divisible by P. Therefore, order of the center is in fact at least P. So in fact, you have to have guaranteed, you have to have at least P minus 1 elements that commute with everything. Okay. Any questions? Okay. And I'm going to finish up the section with this because everything else I'm going to discuss in the homeworks, as a matter of fact. What we discussed, I guess you can kind of gratuitously rip me off there. Okay, any questions? Okay, so now we've seen So what do we have here? We have now sort of in our trick bag, actions of groups on sets, in particular, actions of groups on itself, that's a big one. Or actions of groups on left cosets of the subgroup, actions of conjugates of the group. These are all kind of important types of action. We've also got the class equation and this very important thing about the center not being trivial for a P group. That's going to serve us well. How many of you have seen the Sylow theorems before at some point in the past? Okay, good. So we're going to practice here. And in fact, one of the first things I'm going to do is get so we're going to Cauchy's theorem out of this. So let me start off with this this lemma in this section. I'm going to let G be a finite group. Unless I say otherwise. And P0 is a prime integer. So that's kind of going to be my notation here. But let's do a little bit of a warm up here. Let's introduce the following one. Suppose that origin. So again, we're looking at these P groups here, and G acts on a finite set. So here what we have is we have a group of prime power order acting on some finite set A if A0 is the set of X such that all G and G. Okay, so this A sub 0 is everything in my finite set that's left alone by everything in G. So this is like a super stable set. So no matter what you try to hit things in A0 with, you hit it with anything in G, it just leaves it alone. Then okay, then you can tell something about the number of elements in the set in the first place if you know this. That is to say, the number of elements in A minus the number of elements that are stabilized by everything, the difference in that must be divisible by this prime. Okay. Seems magic, so let's see what we get out of this. No. That's bar. Okay. X is going to be an element of A. I'm gonna denote X bar to be its orbit. So this is actually the equivalence class of A under the action of G. So it's every X times every element of G, that's its equivalence class. This is my orbit here. Notice the number of elements in the orbit of X is equal to 1 if and only if X is in A 0. Everybody agree with me? Because what it means to be an A0 is everything in G leaves it alone, which means its orbit is only X itself. And so what I'm going to do is I'm going to sort of write A as this union of these orbits. So these are all the elements of A, and what I've done is I've really listed the orbits here. And this is similar to what I did to that class equation here. This A0, these are all the elements here that orbit only to themselves. Okay, now let's suppose that there's something that doesn't orbit to itself, like X1. We're looking at its orbit, everything that's equivalent to that, then X2's orbit all the way up to X2. Right? Let me notice that each xi how many elements are in each one of these xi's? Well, what's my favorite thing? This is the old chestnut again. The length of the orbit, and that's what that is. It's the length of the orbit of xi, is the index of the stabilizer. So this should be length of the orbit is the index of the stabilizer. And notice that the order of G is equal to P to the N, and the order of the stabilizer is P to the K, and K is strictly less than N. This is almost identical to that argument that I gave back when we were looking at the class equation. The stabilizer of Xi is a subgroup of G, so it has to be a power of P. It's less than or equal to N. Y is strictly less than, because if it's not, if this is P to the N, that means that Xi is stabilized by everything in G, and so it actually belongs over in A0, not there. All right. Therefore, P divides each one. G makes GXI. So, as P divides right, as P divides each G EXI, then P must divide because this is a disjoint union, P divides the size of all of these, so P must divide the difference in the sizes of these. And so and there's our one. Okay, let me give you the next bit here. This next one, along this line of thinking, and this is kind of a split proof of Cauchy's theorem. I call this Theorem 422. So, Cauchy's theorem. Let's suppose that suppose G is and P is prime. I know I said that was my notation, but I feel it's important to emphasize it here, such that P by 0, then G as an element X such that is X. This is really cool because what it says is if you have a group G and its order is divisible by the prime P, you must have an element of that order. You must have an element of order P. This is untrue if I change almost anything, right? If I change this, if I remove prime, not true, right? For example, Z2, Z2, that has 4 elements, right? There's no element of order 4. Can't do it. And in fact, that actually shows that you can't just change this to a prime power. P to the 1 is important, right? So, and the Sylow theorems, one might argue that the Sylow theorems is a very good attempt to generalize this. Let's go through the proof of this. And this is one of the coolest applications of group actions ever. So what I'm going to do is I am going to let G I don't think I can be more specific here. I'm going to call it S. I'm going to let S be the collection of P tuples of elements of G. Where Xi is in G. I can repeat if necessary, right? So I don't assume they're distinct. And so S is this collection of P tuples that when you multiply the entire tuple together, you get the identity. Okay, first question. How many elements are in S? How will we count this? There's kind of a clever way to count this. I'm gonna make a little bit more. So let me write this here. Put into the order of G. I'm just going to write it as n. Notice the P must divide in. How many elements? How many elements are in this crazy set? Well, let me also point out, it's always good to kind of get your bearings, I think. Okay, this is a silly thing, but let me point out that S is not empty. Right? I mean, that's always good. I mean, I don't want to sit up here and spend the next 15 minutes proving theorem about the empty set. How do I know it's not empty? Right, you can just take identity across the board and it works. Right, so there's at least one thing in there. How many things? Okay, I see. Yeah, but actually, I think you get more than that. Actually,
more than that by just using inverses in the identity and a bunch of different.
What if I told you that? Can you justify that for me? What if it's n to the p minus one?
Are we assuming that P is at least? Or, I mean.
Oh, I
greater
know
than
how
two?
you can do it.
Yeah,
You can do n, so you choose the first p to be whatever, at p minus one to be whatever you want, and then you choose the inverse for the last one.
right. That's right. You've got willy-nilly freedom to do whatever you want to the first p minus one, right? Pick them however you want. But once you do that, this equation forces the last one, right? So you've got complete freedom, so all in elements G over the first p minus one coordinate, and then your last one is forced. So there's only one choice for the last one. Everybody okay with that? Notice that this is not only is this divisible by p, it's divisible by p to the p minus one, right? Okay. Yes.
Yeah, I'm fine.
Okay. So, right. Of course, notice this is equivalent to 0. Right. And that's just because, of course, n is divisible by p. So now I'm going to take this very modest little group of order p, and I'm going to let it act on this set S by doing this. And the way I'm going to act on this is well, I guess it should actually be this one. Wrong. This row here. So in other words, you read whatever this element is, it's ZP, right? And that because it's in ZP, that's why I put a bar on it. And what you do is you shift by K, right? So for example, if this is 0, this should start with A1, right? So you don't shift at all. If this is 1, this should actually shift to start at A2, so it should start at AK plus 1. And this is, for example, if this is P, it should start at A1 again. Right, good. Everybody okay with that? Notice this is well defined because of the fact that this cycle is linked to P and this is P, right? So, for example, if you have two representatives in the same equivalence class of ZP, if you have K bar equaling to K prime bar, that means the difference between K and K prime is a multiple of P, which means when you do K prime on this and K prime on this, it's just a multiple of P and you do the same shit. Everybody okay with that? And it's pretty easy to see that, for example, when you shift it once, for example, if you have K bar is A bar plus B bar, then shifting A plus shifting B is the same thing as shifting A plus B. Everybody okay? This is a group action. Okay, so there's your group action here. Notice that A1, A2, AP, and S0. Remember, that's the stuff that's left alone by everything, if and only if so see if you can check that detail. It's not too difficult to swallow through. And certainly, as you all pointed out to me before, 1, 1, 1 is actually an S0. Right? So well, so the stuff that's frozen is there's at least one thing that's frozen, namely the entry of all identities. And this is by the previous lemma. But we also know that S itself is equivalent to 0 mod P. Therefore, S0 equals 0 mod P and S0. So in fact, there must be at least P elements in P. There exists an element in S0 that is not 1, 1. But if we go back to our notes, that must mean element is X, 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 with X not 1, because of the statement right here. Therefore, X equals 1. Because of the fact that this thing lives in S, that means that the product of all these elements and then makes it equal 1. This is a really cool proof, and it's amazing because you look at this. I don't know about you all, but I look at this proof and I think, well, you know, I'll just get out my tool chest, a pair of pliers, and wrench or something, and fix this and make this true for something other than P. But it's not true. The theorem does not hold true for really anything other than P. Okay. Definitions here. Any questions? In this next definition, I'm not going to require that G is a finite group. We say G is a P group. Yeah. Every X in G has order. Okay, so a P group is a group where every element has order, a power of that prime P specified. It turns out that if you have a finite P group, then the order of that must be order P to the capital N power, right? But this also allows for infinite groups where every element has prime power order. For example, if you take the direct, actually either one, if you take the direct sum or the direct product of implementing copies of Z2, that would be a two group, even though it's not. Fine. Okay. I think I've got time for this. So let me define for you a special kind of P group. And now I am going to revert to phi. So let G let the order G equal P to the AM, where PCD PM 1 and A is greater than 1. A maximal P subgroup G order PA is called a Sylow P subgroup. Now, let me point out here that if I was being super careful here, I would say if it exists, right? Because I am defining so if you have a group of order P to the A, M, and when I say the GCD of P and M is 1, what I mean is I've sucked every power of P out of this that I can and left M sort of naked with no P's left, right? Then a maximal P subgroup of this order P to the A, that's the maximal possible order of a P subgroup, is called a Sylow P subgroup. Now, like I said, if I was super careful, I'd say if it exists, but I'm going to belay saying that because the Sylow theorems are going to tell us that this does exist. You always get one of these maximal P subgroups. So, yes, sir.
Was one of them supposed to be different, the definitions? Not that it really matters. They're both 4.2.3.
Oh, I'm sure the answer to your question is yes.
Just in case I was looking back.
Yes, this is definitely. Here. 425. So again, finite group P to the AM, where GCD of A or M and P is 1, A is at least 1. Then, so let me give you the Sylow theorems here. Number 1, G contains a subgroup order P to the I. For all I between 1 and A, inclusive. And every subgroup of order I is normal. And some subgroup of order P to the I plus 1, where I plus 1 is less than or equal to A. Okay. Number 2. So the first one guarantees you that a Sylow subgroup exists, because in particular, you've got a subgroup for P to the H. Number two, if is a P subgroup and P is a Sylow P subgroup, G, then there is an X in G such that X in G such that H is contained in X G X inverse. So in other words, any P subgroup is contained in the conjugate of some Sylow P subgroup. So all Sylow P subgroups are conjugate. Because just take H to be a Sylow P subgroup, that means any pair of Sylow P subgroups, one of them conjugates the other one. Sounds like transitivity to me. And finally, if K is equal to the number of Sylow P subgroups of P, then K is equivalent by P and K by M. And so we will delve into this. This is an incredibly powerful thing that generalizes Cauchy's theorem in a big, big way. You always have subgroups of order P to the I, always, maybe not elements, but subgroups. The big ones are all conjugate. That's cool. And in fact, this tells you how to count. And then we'll use the Sylow theorems to do some classification. We'll look at specific numbers. Any questions? Any questions out there? Okay, well, don't forget your homework today. Got any questions? I'll be back in my office. Other than that, y'all have a good weekend. See y'all later.